All right, friends, because I forgot to record this lecture during class, I'm repeating it in my office so that I can post it later today. Last time we were talking about first order reaction kinetics that describe the conversion of starting material A into product P with rate constant K. And we said the rate law defines the rate of the reaction as the appearance of product P, or the change in P concentration as a function of time, or dP dt. Alternatively, you can also monitor it by the opposite of the change in A, or the disappearance of A, and that will be equal to rate constant K times the concentration of A. This is called first order reaction kinetics because the exponent on this concentration term is 1. We can separate variables, get all the A terms on one side of the equation, and move dt to the other side, and we get an expression like this, which is a differential equation that we can integrate to get the following integrated rate law, which describes exponential decay. And you can see as time increases, the concentration of A decreases. Now, there are a few more complicated situations that we want to learn how to deal with. And our goal today will be to give you the tools you need to understand understand the assumptions that are behind the derived integrated rate laws for a lot of different situations. And so when you're reading a paper or perhaps studying a reaction, you know the kinds of considerations you need to make. So let's now deal with second order kinetics. So this will be a reaction where two molecules are involved, and I'm describing reactions that are just a single concerted elementary step, no intermediates. And again, we'll talk about rate constant K. The appearance of product as a function of time is equal to rate constant times concentration of A times concentration of B. Now, you can use calculus and integral tables and differential equations to use this expression and derive a rate law, which I will write here, but you will see is rapidly complicated enough as to not be that useful to us. So if you know the starting concentration of B and the starting concentration of A as indicated by these subscripted zeros, then if you take the natural log of the following expression, starting concentration of A times actual concentration of B as a function of time, divided by starting concentration of B times the actual concentration of A as a function of time, and that gives you, that is equal to rate constant times time. Now, notice what this, if you were going to fit data to this equation, you would need to be able to monitor two things at once. First, you would need to be able to monitor the real-time concentration of A, and second, the real-time concentration of B. And that may not be practical under a lot of different conditions. And so we can simplify by using a pseudo first order reaction conditions. And what we mean by this is that we are going to use an excess, by which we mean greater than 10 equivalents of B relative to A, such that the concentration of B remains constant. And we'll run these reactions not to completion, but just long enough to be able to measure a rate and a rate constant. And and well, friends, sorry, lost my train of thought. Um, so we're going to use an excess of B relative to A such that the concentration of B remains constant. Under those conditions, the concentration of B is going to be basically equal to our starting concentration of B. And remember, again, we're not going to let the reaction run to completion. We're going to do these experiments, do an experiment under such conditions that B doesn't change very much. All right, so let's talk about what that would do. Under those conditions, we could write the rate law as K times concentration of B times concentration of A, but this term is going to be mostly constant, and so we could instead rewrite the rate law as K obs times the concentration of A, where K obs is equal to our actual rate constant times the constant concentration of B. Okay, so in that way, we can find an observed rate constant, and we can run the reaction under such conditions that the reaction will have a first order dependence on A. So we'll see just regular exponential decay, and we can fit that to our expression where exp is the exponential, or e raised to this number, and we can measure the resulting rate constant, which will be K obs. Now, what if I am not satisfied with K obs, but I want to get to the actual rate constant? That's when I can do the experiment under multiple actual concentrations of B. So perhaps I start out at 1 millimolar, 2 millimolar, 4 millimolar, 10 millimolar, 20 millimolar, and I monitor dp dt as a function of time, and then I use that information to calculate for each of those experiments an observed rate constant. Okay. And we won't say what these are, but if I run this experiment under multiple concentrations of B, and then I plot my observed rate constants, I should get a more or less linear relationship, provided that the reaction is first order in B. And we showed that should be the case here by telling us that the actual rate constant K, the observed rate constant, is the product of rate constant and concentration of B. So if I fit the various K obs values versus concentration of B to a line, the slope of that line is going to be my actual rate constant. And so people do experiments under these conditions all the time as a way of simplifying a reaction. And of course, I could go back now and keep A constant and measure K obs when I'm keeping A constant, and then I could do a similar type of experiment, and that would demonstrate first order dependence in A as well. Okay, so that's pseudo first order kinetics is a common strategy that's used to simplify some complicated situations. All right, next we're going to talk about some different scenarios. And these are scenarios where we have intermediates. So, but actually first, let's consider, what if I did this experiment I did this same experiment. I keep B constant and I do the fitting of AE to the E minus K obs times T, and then I plot K obs times K obs versus concentration of B. And what if I see a plot that's nonlinear? Then it would mean that this would suggest non-first order behavior in B concentration. So could the reaction be second order in B? Well, we could try by plotting K obs versus B squared, and if that were linear, that would suggest that our reaction was second order in B. Now, there are some reactions where instead of seeing K obs increase monotonically in a linear fashion or increase quadratically as we change the B concentration, sometimes we observe what is called saturation behavior. That is, we do first order reaction kinetics and we can vary the concentration of B. And at first we see a linear dependence of K obs on B, but after a while it sort of tails off and plateaus. Beyond a certain point, further increases in B do not increase the rate of the reaction. And so saturation behavior suggests a more complicated mechanism. So I want to show you the kinds of mechanisms that can have saturation behavior, and we'll talk about what the implications of that is. The simplest example is just a starting material in equilibrium with a high energy intermediate that then undergoes a second reaction with molecule B with some rate K2 to give product. All right, and we'll start writing the rate law by saying that the rate of product appearance dP dt equals K2 times the concentration of I times the concentration of B, where I is a high energy intermediate. Okay, so we're talking about a reaction that has an energy diagram somewhat like this, where here is A equilibrium with a high energy intermediate, which then combines with B to give us low energy product. And we're going to say that the reaction is irreversible in the sense that there's no, the backwards rate constant is basically zero. All right. Because I is a high energy intermediate, we would expect the forward rate to be slower than the reverse rate, and therefore that the concentration of I is very small. If this were a high energy, for example, carbocationic intermediate, that would make sense, right? But if the concentration of I is already small, variation in that concentration as a function of time must also be very small. In fact, we're going to say it's small enough as to be basically equal to zero. And this is what is referred to as the steady state approximation. Steady state approximation is that the concentration of that high energy intermediate does not change over the course of the reaction. Now, of course, at the end, and at the very beginning, and at the end, that's not going to be exactly true. But during the course of the reaction, when we can make measurements, it's going to be close enough to be hopefully close enough to true to apply. So with that in mind, we can do the following bit of mathematical trickery. di dt equals 0. And now we're going to add up all the things that contribute to the concentration of I increasing and subtract all the things that lead to the concentration of I decreasing. For example, I appears as A converts to I through rate constant K1. So we're going to put K1 times A here. Now, I can disappear in two different ways. I can either go back to starting materials via the K-1 process, which is K-1 times I, or I can disappear to form product, and that's K2 times I times the concentration of B. Now, I can separate variables, get all the terms that contain I on one side of the equation and all of the terms that contain A on the other side of the equation. Then I can factor out the concentration of I to give me the following quantity in parentheses. And then I've got an expression for the concentration of I that depends on rate constant 1 times concentration of A, and then in the denominator we have K-1 plus K2 times B. All right, that's simple enough. Now let's plug this expression for I back into our rate law here. In other words, we can now say that dP dt equals K2 times K1 times the concentration of A times the concentration of B divided by K-1 plus K2 times B. And this is a typical rate law for situations where you go through a high energy intermediate and you get a steady state approximation. Now let's describe what this equation tells you about the reaction. First, the reaction you can see is first order in A, meaning that the rate depends linearly on A. But the reaction is more complicated in its dependence on B. If B is large, then we would expect K2 times B to be much greater than K-1. And if that's true, then we can make the approximation that the rate of the reaction is equal to the following. K2 times B, and then the B concentration term and the K2 terms factor out, and we're left with a more simplified expression that's just K1 times A. So under those conditions, we would see a reaction that is first order in A and 0 order in B. This would be, this situation is what we see here in the saturation regime, where increasing the concentration of B doesn't change the rate of the reaction. In other words, this reaction is so fast that the only way to accelerate it is not to add more B, but rather it depends on the appearance at the intermediate. Now, we can think of another set of conditions. What if the concentration of B is small, or perhaps and K2 times B is much less than K minus 1. Under those conditions, you can approximate the rate law as the following. K2, K1, A, B divided by K minus 1, which would be basically the same as observed rate constant times A times B. So under those conditions, we would see that the reaction is first order in A, and then also first order in B. All right. So you can see that this situation would be in the sort of linear regime where increasing the concentration of B increases rate linearly. All right. So all right, let's describe a slightly more complicated situation that we can treat with steady state kinetics. And this is going to be the SN1 reaction. Let's use this alkyl bromide, and we will have some process whereby the alkyl bromide becomes the carbocation and Br minus. And we'll call this starting material A, intermediate I, and we'll call Br minus maybe product 1. And then I reacts with B, which in this case is going to be our nucleophile. Suppose for our purposes this is, I don't know, let's just choose Cn minus. And that reacts with rate constant K2 in an irreversible fashion to give us our product 2. All right. Now you may be asking at this point, why are we doing this? We learned in undergrad OChem that SN1 is unimolecular, that its rate only depends on the concentration of alkyl halide starting material and not on the concentration of the nucleophile. Well, what you learned was true from a certain point of view, or rather true under certain conditions. But let's see how and when those conditions apply. So as before, we're going to say that we're going to make the steady state approximation that the rate of change in the concentration of I, intermediate I, carbocation, is equal to 0. We're going to add up all of the things that can generate intermediate I, and that's only this K1 step, because we're saying that the reaction is basically irreversible, that K minus 2 is basically 0. So K1 times A gives us I, and then I can disappear in two different ways. It can disappear by having intermediate I recombine with product 1, which is the bromide, to go backwards, or it can, the concentration of I can decrease as I combines with B to give me product. Now, the overall rate of the reaction will be as monitored by the appearance of product 2 is going to be equal to K2 times intermediate I times B. All right. So now we're going to do the same thing. We're going to, as we did before above with the steady state approximation, we're going to separate terms and divide both sides to, we're going to separate terms, factor out I, and then divide both sides by the same quantity to get the following expression: K1 times A in the numerator, and then in the denominator, we're going to have K minus 1 times product 1 plus K2 times B. And if we plug that into our rate law as indicated there, we're going to see that dP dt is equal to K2 times K1 times A times B divided by K minus 1 times P1 plus K2 times B. All right, so there are a couple of interesting features of this SN1 reaction. Let's ask the question, under what conditions would the reaction be zero order in B? Well, as we saw before, if the K2 times B term is greater than the K minus 1 times P1 term, then we can rewrite our rate law as K2 times K1 times A times B divided by K2 times B. And as we did above, the K2 terms cancel out, the KB terms cancel out, and we're left with K1 K1 times A as our expression for the reaction. So this would be sort of classical first order reaction conditions for the SN1 reaction. How can K2 be bigger than the K2 term be bigger than the K minus 1 term? Well, one way is for the B concentration to be large. Another is for the K2 term to be fast. All right. Well, okay, so that's one feature. The reaction is zero order in B as the concentration of B is large, or if K2 is fast. Notice that the reaction is always first order in A. What about this product term in the denominator? What would happen as the if the product term increases. For example, what if you supply added product 1? For example, what if I did this reaction and I added some Br minus into the reaction mixture? Well, under those conditions, if K minus 1 times P1 is greater than K2 times B, and again, this could be because P1 is larger or K minus 1 is fast, then I could rewrite the rate law. Appearance of product 2 is equal to K2 times K1 times A times B divided by K minus 1 times P1. And this situation is first order in A concentration. It's also first order in B, and it's inverse first order in product concentration. In other words, if we increase product 1, the rate, concentration of product 1, the rate of appearance of product 2 decreases. And this situation is often called product inhibition. And it sort of makes sense if I, based on the reaction scheme shown up here, if I add lots of Br minus, that's going to start competing with the Cn minus to react with the high energy carbocation. And product inhibition is a feature of a lot of different situations, especially in enzyme chemistry. All right. Lastly for today, we're going to talk about a situation that's called rapid prior equilibrium. All right. So let's go through this in a little bit more detail. So we're going to talk about this situation. What we mean by prior is before the irreversible step and faster than subsequent steps. So the rapid prior equilibrium situation involves the steady state approximation, but it also allows you to make some simplifying assumptions. So what I'm going to show you now is a particular kind of SN2 reaction. I'm sorry, an SN1 reaction. We're going to start with alkyl halide molecule R, and it's going to react with H3O plus, and there's going to be a forward and a reverse rate there, where my equilibrium constant is Kf divided by Kr. That will give me a protonated alcohol and water. And then I will have the leaving group leave. And this is a K1, K minus 1 situation. Water leaves to give me a carbocationic intermediate, which I am going to call I. This protonated alcohol I'm going to call RH plus. I is the intermediate, and then we're going to have that intermediate combine with a nucleophile. Let's have it be Br minus via some process K2 to give me the substitution product shown here. All right. So we'll just call this product P. Now, let's look at this first equilibrium expression. R plus hydronium goes to protonated alcohol RH plus and water. Well, this is just an acid-base equilibrium, and we could say that KEQ for that reaction is equal to the concentration of RH plus times the concentration of water divided by the concentration of R times the concentration of H3O plus. Right? We'll just call this equilibrium constant K. Now let's try to calculate an expression for RH plus that is, and these are, what we're saying is these are always in equilibrium. This equilibrium step is fast enough that as soon as we remove this, we go back into equilibrium. So we can say that the concentration of RH plus is always equal to the forward rate times the reverse rate times the concentration of R times the concentration of H3O plus divided by the concentration of water. All right. But then I need to remember the definition of the acid dissociation constant, Ka, which equals the concentration of RH plus the Ka for the protonated alcohol is the concentration of RH plus, acid dissociation constant for this reaction. And it turns out that, I'm sorry, I'm struggling with a way to explain this. Everything we've done up to this point is fine. But if we reformulate the expression like this, K reverse, K forward, and then OH here and water there. I'm sorry, hydronium here. This is RH plus and this is R. The equilibrium constant for this reaction should be Kr over Kf, and that's going to equal the concentration of alcohol R times the concentration of H3O plus divided by the concentration of RH plus times the concentration of water. And if we multiply both sides by the concentration of water, we end up with KEQ times the concentration of water, or our acid dissociation constant, which equals R times H3O plus divided by RH plus. All right, so then we can also write the concentration of RH plus as being equal to concentration of R times concentration of H3O plus divided by Ka. All right, and then we can, and that we're going to say that This is always true because this equilibrium is fast. So if you follow through, what we've done here is exactly the same as what we did up there. But this is a way to simplify things. So all we need to know is the starting alcohol concentration, the pH of the solution, and the Ka of the protonated alcohol. From then on, we can do a steady state approximation based on our intermediate I. So again, we will say that di dt equals 0, or in other words, and now we need to talk about all of the things that lead to I. K1 times the concentration of RH plus leads to intermediate I. K minus 1 times the concentration of intermediate I times the concentration of water leads back to protonated alcohol. And then the next term that reduces the concentration of I is K2 times I times Br concentration. All right. And with that in place, we can separate variables and isolate, factor out I, and divide both sides by the same quantity. We come up with K1 times RH plus divided by K minus 1 times the concentration of water plus K2 times the concentration of Br minus. And then we can take our overall expression for the rate of this reaction, which would be dP dt equals K2 times I times Br minus concentration. To rewrite our rate law like this, K2 times K1 times concentration of protonated alcohol times the concentration of Br minus divided by K minus 1 times the concentration of water plus K2 times the concentration of Br minus. And I've already got an expression for protonated alcohol that I can write simply in terms of things that are going to be constants, or rather things that I can know. I can know what my starting concentration of R is, and I can know what Ka and what pH is. So I might rewrite this expression as K2, K1, and then we'll say Ka to the negative 1 times R times H30 plus times Br minus. And then we'll divide that by K minus 1 times H2O plus K2 times Br minus. Okay. So let's talk about a couple of different scenarios here. Again, you would expect a couple of features. First, you expect to see product inhibition. If the concentration of water is high, then this term will overwhelm that one. The reaction will be first. This term will overwhelm that one. The reaction will be first order in alcohol, H3O plus and Br minus, and be inverse first order in water concentration. So we expect to see product that is H2O inhibition. And again, this makes sense. If we have large amounts of water, that should push the reaction backwards this way. Second, so that's one feature, we expect to observe saturation kinetics in Br minus. That is, if the concentration of Br minus is high, then the K2 term will overwhelm the K minus 1 term, and then you're in a similar situation. Then the bromine terms and the K2 terms would cancel out, and then dP dt is basically going to be K1 times Ka minus 1 times R times the concentration of H3O plus, where the K2 and Br terms have canceled out. And so 2 is likely the situation we're in as we try to do an SN1 reaction to convert a tertiary alcohol into a tertiary bromide. We see that the reaction depends on the concentration of water, of hydronium, and the concentration of alcohol no matter what. And then if the concentration of Br minus is large enough, then the reaction is zero order in Br minus. All right, so those are our scenarios, and that takes us up through, in fact, even a little bit past what we did in class today. So we'll go through some of this in the next lecture, and we'll try our hand at a couple other situations, and then we'll move on to the last part of Chapter 7.